Hi guys, welcome back to Technovizard. So you can join us on Facebook, Instagram, Telegram, YouTube for the latest job notifications. So let's get started. So this is our first question. What is the characteristic impedance Z naught of a line having the resistance R, inductance L, capacitance C, and the conductance G? So basically, this is a power system question in which we have to find out the characteristic impedance Z naught of a transmission line. So we know that a transmission line is represented like this is R, this is L, and in parallel we have C and the conductance G. So this is the equivalent electrical equivalent model of a transmission line. Okay, so this is R, L, C and G. So now we have to find out the value of the characteristic impedance. So the characteristic impedance Z naught is given by square root of Z by Y, and where Z is equal to R plus J omega L divided by Y is G plus J omega C. Okay, so characteristic impedance is given by R plus J omega L divided by G. So option A is correct. Also, for the transmission line, if we have to calculate the propagation constant, so propagation constant is given by gamma, which is equal to alpha plus j beta is equal to, this is j beta, and this is equal to square root of z into y. Okay, so this is the formula for the propagation constant, but in the question they have asked the value of the characteristic impedance, so option A is correct. So next question is, a parallel circuit has the two branches. In the one branch, R and L are in series, and in the other branch, R and C are in series. The circuit will exhibit the unity power factor. It means unity power factor. It means the circuit is purely resistive. It means the circuit is under the resonance. Okay, so here we are having the two branch. In the one branch we have R and L, in the other branch we have R and C, the connected series. So this is R, C, R and L. So now the circuit will be under resonance when, suppose this is resistance R1. So when R1 is equal to resistance R2, this is equal to L by C. So here R1 and R2 value are same, so this is equal to R is equal to root L by C. Okay, so option A is correct. And for this circuit, if we have to calculate the resonating frequency, which is given by omega naught, which is equal to 1 by root LC, so this formula is valid when R1 is equal to R2, then this formula can be used for the resonating frequency. Okay, so option A is correct. Next question is, a parallel circuit consists of two branches, one with a pure capacitor and other has a resistor of 5 ohm in series with a variable inductor. To this circuit, an AC voltage of fixed value in the frequency is connected. The circuit will exhibit the two resonances if, so here the circuit will exhibit the two resonances. So let's first draw the circuit. So here we are having a resistance R and a variable inductor. So this is variable inductor, the resistance value is 5 ohm. It is connected in parallel with a pure capacitor. So suppose this is C and this is L. Okay, so now we have to find out the value of the reactance of the capacitor value. Okay, so let's first calculate the Z equivalent. Okay, so Z equivalent for this circuit is given by, so Z equivalent, so suppose the impedance of this branch is Z1 and the impedance of this branch is Z2, so they both are connected in parallel. So the Z equivalent is given by Z1 Z2 divided by Z1 plus Z2, as they are connected in parallel. So Z equivalent will be, so Z1 is R plus J XL, so this is R plus J XL into Z2 branch is capacitive, which can be written as minus J into XC divided by R plus JXL minus JX into C. So let's simplify this. So Z equivalent is given by, and this will be R plus JXL into minus JXC. In the denominator I am taking plus j common, so this will be xl minus xc. Now let's rationalize this equation. So let's multiply r minus j xl minus xc divided by r minus j xl minus xc. Okay, so now let's simplify. So this will be, so let's first simplify this. So this will be minus j r into xc. So j square is minus 1, so this will become plus xl into xc, and this will be r plus j xl minus xc into r minus j xl minus xc divided by r minus j xl minus xc. Now, so now the denominator is of the form a plus b into a minus b. So this is a plus b into a minus b, which is equal to a square minus b square. Okay, so we will write in this form, and let's simplify this equation. So let's multiply this. So this will be minus j r square into xc. J square is minus 1, so this will become minus r into x of c into xl minus xc. So let's write here. So this z equivalent will become, so this will be equal to minus j r square into x of c, then minus r into x of c, this is xl minus x of c, then plus r xl xc, and minus j, this is xl minus xc into xlxc divided by a plus b into a minus b is of the form r square plus xl minus xc whole square. So now let's take the imaginary term common. Okay, so we know that the circuit will be purely resistive, so for the purely resistive only r will be present. It means the imaginary term of z equivalent will be equal to 0. So let's take the imaginary term first common. So I am taking minus j common, so this will be r square into x of c. So here no imaginary term, here also no, I have taken minus j common, so this will be plus, let's multiply this. So this will be xl square, so this is xl square into x of c, I have taken minus j common, and this will be minus xl into xc square divided by denominator is r square plus xl minus xc whole square is equal to 0. So now this will be r square x of c plus xl square x of c minus xl x of c square is equal to 0. So let's take x of c common on both the, from both the sides. So this equation left will be r square plus xl square minus xl xc is equal to 0. So this is of the quadratic equation, this is xl square minus xc into xl plus r square is equal to 0. So let's compare this quadratic equation with the characteristic equation, which is of the form s square plus 2 zeta into omega ns plus omega n square is equal to 0. So this is the characteristic equation where omega n is the natural frequency and zeta is the damping factor. Okay, so now after comparison here, so therefore we are getting the value of omega n is equal to r after comparison, and here in place of s we have x of l. So this implies that 2 zeta into omega n, so 2 zeta into omega of n is equal to minus x into c. So from here we are getting the value of zeta as minus x of c divided by 2 into omega n, so this is equal to minus x of c divided by 2, and x omega n value is r, so this is equal to minus xc divided by 2r. Now Now in underdamped system, so in we know that the in the underdamped system more than one oscillations are present. It means zeta will be less than 1. This is the condition for the underdamped system. It can also be written as zeta is less than -1, and now we have calculated the value of zeta as minus x of c divided by 2 into r is less than -1. So let's multiply -1 on both the sides, so the sign will get changed. So this will be x of c will be greater than 2 into r, and in the question the value of resistance r is given as 5 ohm. So we are getting the value of x of c is greater than 10 ohm. Okay, so it means the reactance of the capacitor is greater than 10 ohm, so option b is correct. Okay, so next question is, in the circuit shown in the figure, what value of C will cause a unity power factor at the AC source? So unity power factor, it means circuit must be purely resistive. So now here this C and this ZL branch is connected in parallel. So let's calculate the admittance of the branch. So whenever they are connected in parallel, so we prefer to go with the admittance. So let's calculate the total admittance of the circuit, which is given by Y is equal to Y1 plus Y2. So Y1 is equal to 1 by Z1, okay, plus this is 1 by ZL. Okay, now this Z1 can be written as 1 by j omega c. So after simplification, y we will get, so this will go in the numerator, this will be j omega c plus 1 by ZL. Value given in the question is 30 angle 40. Okay, so this will be equal to 1 by, oh, so this will be y is equal to j omega c plus, so 1 by 30 is 0.033, and this will 40 will go in the numerator, it will become -40. So now let's expand this. So we are getting the value of y as j omega c, so this will be 0.033. Cos -40 is cos 40, but sin -40 is minus sign, so this will be j 0.033 sine 40. So let's simplify. So from here we are getting the value of y as j omega c. So after simplification of this, we are getting 0.0255 minus j 0.0212. So now let's separate the real and the imaginary term. So this will be 0.0255. So I'm taking j common, so this will be omega into c minus 0.0212. So now the circuit will have the unity power factor, it means only the resistive r term will be present, so imaginary term of y will be equal to 0. So let's equate this term equal to 0. So under the resonance, imaginary term of y is equal to 0. So we are getting omega into c minus 0.0212 is equal to 0. So from here we can calculate the value of c as 0.0212 divided by omega, and this is equal to 0.0212 divided by omega is 2 pi into frequency is 50. So this is equal to 0.0212 divided by, this will be equal to 314. So from here we are getting the value of c nearly equal to 68.1 microfarad. Okay, so 68.1, so option A is correct. Okay, so next question is, the resonant frequency of the given circuit will be, so now here we are having an inductor and C and R are connected in parallel. So we have, let's first calculate the input impedance of the circuit. So here this Z will be equal to, this is inductor which is connected in series, so this will be j omega L plus resistance R is in parallel with 1 by j omega c. So this can be written as j omega L. So this will be plus R into 1 by j omega c divided by R plus 1 by j omega c. So this Z will be equal to j omega L, and after simplification we will get R divided by 1 plus j omega c r. Okay, after simplification of this. So now let's substitute the values of r, l and c. So this is L value given in the question is 0.1 plus r is 1 divided by 1 plus j omega, and c and r value is 1. So now let's rationalize this term. So this will be 1 minus j omega divided by 1 minus j omega. So this will be equal to j 0.1 omega, and this will be plus 1 minus j omega. So this will be a plus b into a minus b is equal to 1 plus omega square. So now let's take the LCM as 1 plus omega square. So this will be equal to j 0.1 omega into 1 plus omega square plus 1 minus j omega. Okay, so now this can be written as 1 minus j omega plus j 0.1 omega into 1 plus omega square divided by 1 plus omega square. So now let's take j common from here. So this is 1 plus, so I am taking j common. So this will be equal to 0.1 omega into 1 plus omega square in minus omega divided by 1 plus omega square. So now circuit is under the resonance, it means the imaginary term of z is equal to 0. So this implies that 0.1 of omega into 1 plus omega square minus omega is equal to 0. So this means 0.1 omega of 1 plus omega square is equal to omega. So this will get cancelled. It means 1 plus omega square is equal to 1 by 0.1, which is equal to 10. It means omega square is 10 minus 1 9. So omega we are getting as 3 radian per second. Okay, 3 radian per second. So option C is correct. Next question is, consider the following statements S1 and S2. S1, at the resonant frequency the impedance of a series RLC circuit is 0. So this statement is wrong, because in a series RLC circuit under the resonant frequency the impedance is minimum, okay, which is given by Z minimum is equal to R. So this is S1 statement, and if impedance is minimum, as a result of which the current will be maximum in the series RLC circuit, which is V by R, and the circuit will be purely resistive, hence it will have unity power factor. S2 statement is, in a parallel GLC circuit, increasing the conductance G results in the increase in its quality factor. So basically in S2 statement we know that the quality factor for a parallel RLC circuit is given by R root C by L. Okay, so resistance R in terms of conductance can be written as 1 by G root C by L. Now if we will increase the conductance value G, the quality factor will decrease, but in the question it is saying quality factor will increase. So this statement is also wrong. It means both the statements S1 and S2 are false. So option D is correct. Okay, so next question is, for a parallel RLC circuit shown, if R is equal to 10 ohm, L is equal to 0.1 Henry and C is equal to 0.1 Farad, the current I is sinusoidal of frequency equal to the resonant frequency of the circuit. It means this circuit is under the resonance, already mentioned in the question. Okay, so when the circuit is under the resonance, so the condition is given by BL is equal to BC. It means the inductive susceptance is equal to capacitive susceptance, and the circuit left will be purely resistive. It means the inductor and capacitor will nullify each other effect and the circuit left will be purely resistive. Then the current through the resistor R will be nothing but this I current will flow through the resistor R. So option C is correct. Okay, so next question is, a circuit has two parallel branch. In one branch R and L are connected in series while in other R and C are connected in series. If R is equal to root L by C, which of the following is not correct? Okay, so this is R, the L, and here we have R and C. So in the question it is saying that R is equal to root L by C. We know that this is the condition for the resonating circuit. So now if this condition is satisfied, it means the circuit is in the resonance. So this statement is right. Now the two branch currents are in the quadrature. Okay, so let us suppose the current in the RL branch is I1 and the current in RC branch is I2, and here the total voltage applied is V, and suppose the total current of I is flowing. Okay, so now if this condition is satisfied, so now let us draw the phasor. So suppose this is voltage V. Okay, and if this is, suppose this branch is purely inductive, then this I1 current must have lagged the voltage by the 90 degree, but here the R is also present, this is RL. It means the current I1 will be lagging V by some angle theta 1. I am denoting. Okay, so this is I1 and this is I2, and in I2 the current will lead the voltage by some angle theta 2. So this will be something like this. Okay, it will not lead by 90 degree because R is present, so this is leading by theta 2. Now here the angle between the I1 and I2 will be 90 degree. It means the two branch currents are in the quadrature forming a 90 degree. Okay, so it means the two branch current are in the quadrature. It means the angle between the current I1 and I2 is 90 degrees. So this statement is right. Next is, the circuit has an impedance independent of its frequency. So we know that when the circuit is under the resonance, the circuit will be purely resistive and the resistance does not depend on the frequency. So this statement is right. So next statement is, the two branch currents are in phase. So this statement is wrong because the two branch current are in quadrature. The overall current, which is current I, will be the phasor sum of I1 and I2. So let's draw. So this is current I2 extended and this is I1. So the total current I is a phasor sum of I1 and I2, so this will be in phase. So this means the total current will be in phase, not the two branch current. Okay, so this statement is wrong, and in the question it is asking the non-correct statement, so which is option D. So option D is correct. Okay, so next question is, a parallel circuit consists of two branch. One branch has R, L and L connected in series and the other branch has R, C and C connected in series. Consider the following statements. So now so this is R of L, this is L, and this is R of C, and this is C. So now in the question it is saying that the two branch current I1 and I2 will be in quadrature. It means it will form a 90 degree when RL into RC is equal to L by C. So we know that the circuit will be under the resonance when RL is equal to R of C is equal to root L by C. So now let's multiply both of them. So RL into RC, we are getting L by C. So this statement is right. So when this condition is satisfied, then the two branch current will be in quadrature. So this statement is right. Next is, the impedance of the whole circuit is independent of the frequency if RL is equal to RC, and if RL is equal to RC is satisfied, then the resonating frequency will be given by 1 by root LC. So this statement is also right. So the impedance of the circuit will be independent of frequency because the circuit will be purely resistive. Next statement is, the circuit is in the resonance for all the frequencies if RL is equal to RC. So this statement is wrong because if RL is equal to RC, then the circuit will be at the resonance only at the resonating frequency. It will not be at the resonance for all the frequencies. So this statement is wrong. Next is, the two branch currents will be in phase. Wrong, because the two branch currents will be in the quadrature at this. So if omega is this, then the two branch current I1 and I2 will be quadrature, previously explained. So correct statement are 1 and 2, so option A is correct. Next question is, consider the following circuit. For what value of omega the circuit shown above exhibit the unity power factor. Okay, so now let's calculate the impedance of the circuit. Okay, so here R and C are connected in series, which is in parallel with L. So now let's calculate the impedance of the circuit, which is given by, so this will be R minus jx of C, which is in parallel with j of xl. So now let's simplify this. So this will be R minus jx of C into jxl divided by R plus j, I have taken common, xl minus xc. Okay, so now let's rationalize this also. So this will be R minus j xl minus xc divided by R minus j xl minus xc. So this will become, so z is equal to, so now let's simplify this. So this will be equal to, so let's multiply this. So this will be j, and this will be r square into xl. So this is j into r square xl, and this will be plus r xl into xl minus xc plus r xc into xl minus j xl xc into xl minus xc divided by a plus b into a minus b is a square minus b square is r square plus xl minus xc whole square. So now let's take the imaginary term common. So I'm leaving the real part plus I'm taking imaginary term common. So this will be r square into x of l. Okay, and here I've taken j common, so this will be minus xl into xc in bracket xl minus xc divided by r square plus xl minus xc whole square. So now circuit will be unity power factor. It means imaginary term of z should be equal to 0. So now let's equate. So imaginary term of z is equal to 0. So we are getting r square into x of l minus xc into xl into xl minus xc is equal to 0. So now let's expand this. So this will be r square into xl. So this will be minus xl square into x of c. So this will be plus xl into x of c square is equal to 0. So now this can be written as, so x of l is omega into l minus xl square is omega square l square divided by x of c is omega into c. So this will be x of l is omega into l divided by omega square c square is equal to 0. So this will be, so we are getting r square omega into l minus omega l by c plus l by omega into c square is equal to, so this is omega l square. Okay, this is equal to 0. So now let's take the LCM as omega c square. So this will be r square omega square l into c square. This will be minus omega square l square c, and this will be plus 1 is equal to 0. Oh sorry, this is l. So now I am taking omega square common from here. So this will be omega square I have taken common. So this will be r square l c square minus l square c. So this is l will go on the right hand side, will become minus l. So now omega square is equal to minus l divided by r square l into c square minus l square into c Okay, so now this is minus L, I am taking minus L common. Okay, so this will be L into C minus, I have taken common, so this is minus R square into C square, so this will get cancelled, so this will be equal to 1 by L into C minus R square C square. So now we have to calculate the value of omega. Okay, so it means omega is equal to 1 by root LC minus R square C square. So option B is correct. Okay, 1 by root LC minus R square C square. So option B is correct. Next question is, for the circuit shown in the given figure, what is a natural frequency? So in the circuit, you can solve this question similarly. You have to calculate the impedance, so I'm directly writing the formula for the natural frequency. So natural frequency is given by omega into n, which is simply equal to 1 by root LC, which is the formula for the resonating frequency. We know that omega is given by 1 by root LC, which is the resonating frequency. Now let's substitute the value of L and C, which is given by, so L value given in the question, so this is L and this is C. So this is 400 into 10 to the power micro is 10 to the power minus 6 into 100, and pico is 10 to the power minus 12. Okay, so we are getting this is equal to 1 by, this is equal to 4, and this will be equal to 10 to the power, this is minus 18 plus, this is minus 18 plus 4 is minus 14, so this is 10 to the power minus 14. So let's simplify, so 1 by root 4, this will 2, and this is 10 to the power minus 7. Okay, so now this 10 to the power minus 7 will go in the numerator, so this can be written as 10 into 10 to the power 6 by 2, which is equal to 5 mega, and this is radian per second. Okay, this is omega into n, so option D is correct. Next question is, so the resonant frequency for the circuit for L is equal to 0.2 Henry, R is equal to 1 ohm, and C is equal to 1 farad is, so basically we have to calculate the resonating frequency omega. So similarly you can write the expression for the input impedance and then equating the imaginary term to 0, you will get the expression for the omega for this question will be equal to, so omega square is given by C into R square minus L divided by, so omega square is equal to C R square minus L divided by L into C square R square. So now let's substitute the value. So C value given in the question is 1, R square is 1 minus L value given in the question is 0.2 divided by, this is 0.2 into 1 into 1. Okay, so 1 minus 0.2 is 0.8 divided by 0.2, so we are getting omega square is equal to 4. It means omega is equal to 2 radian per second. So option B is correct. Next question is, the value of Z in the given figure which is most appropriate to cause a parallel resonance at 500 Hz. Okay, so now we have to cause a parallel resonance. So here in the question R is given, L is given, so it means this Z should be of the capacitive nature, then only the parallel resonance will be possible. So it means this Z is capacitive. Okay, so now we have to calculate the value of Z. So let's first calculate the admittance of these two parallel branch. Okay, so now suppose the admittance is given by y1 plus y2. Okay, so which is equal to, so y1 is 1 by z1 plus 1 by z2, so this is equal to, this z1 is this, so this can be written as j omega L, and this is capacitor, so this is 1 by j omega C, this will go in the numerator, this is 1 by j omega C. Now let's take the LCM as j omega L, so this will be 1, this will be minus omega square L into C. Okay, so now let's rationalize. So after rationalize we will, so this j term will go in the numerator, this will become minus j, this will be 1 minus omega square L into C divided by omega into L. So we know that the imaginary term of y should be equal to 0. It means 1 minus omega square L into C is equal to 0. So now it means now we have to calculate the value of C. So it means omega square is equal to 1 by L into C. So let's calculate the value of C, which is equal to 1 by L into omega square. So this will be equal to, so C is equal to 1 by L given in the question is 2 and omega is 2 into pi. Frequency is 500 square, which is the resonating frequency. So after the simplification we are getting the value of C as, this will be equal to 1 by 2. So this will be equal to 1000 pi square and pi is 3.14. So this will be equal to 2 into 3140 square. So this is equal to 0.05 microfarad. Okay, so this is the value of C. So option D is correct. Next question is the value of the capacitance C in the given AC circuit to make it a constant resistance circuit, or for the supply current to be independent of its frequency. It means the circuit is under the resonance and here R and L are connected in series and RC are connected in parallel. So for this circuit the condition for the resonance is given by when R1 is equal to R2 is equal to root L by C. So here R1 is equal to R2 is equal to 4. So this means 4 is equal to L value given in the question is 1 divided by C. So now squaring on both the sides, so this will be equal to 16 is equal to 1 by C. So from here we are getting the value of C as 1 by 16 farad. So option A is correct. So yeah, thank you guys for watching this video. See you in the next lecture.